Okay, yeah, nice, sure. Okay, so saying there are two methods in which we deal with the position vectors. In one way, you have 2 points, A and B. So let's say A has coordinate AX, AY, and AZ. And then you have another point B, which has coordinates BX, BY, and BZ. So if you wanted to find the position vector or the displacement vector from A to B, you know to say this is going to be, you are ending at B, you're starting from A. So this is going to be BX minus AX. This is going to be giving you I. Then plus BY minus AY. This is going to give you J. Then just like that, you have BZ minus AZ. This will give you K. Now, this is one way of doing it. But if you have, let's say, something like this, and then you have the 2 points, one is somewhere here and the other one is somewhere here, you can use the same thing to say that you express A in terms of its components and B in terms of its components. Or you can just look at how you are moving from one point to the other, which is the most straightforward approach. But whichever method that you understand better, I will demonstrate both methods. So I think for the second method, it's best when I have exact coordinates so that I show you how I actually make the steps, which I'm going to do using the first question. So take, for example, a question like this one. Let's get this. Let's take it down. So take, for example, a question like this one. In this question, what do they want us to do? Well, they're saying determine the expression for the magnitude FCD. The magnitude of the, determine the expression for the magnitude FCD of the component of F along the line CD. So they want to find the component of a force F. A force F is this side, but they want to find its component along the line CD, along that line. How do we do that? Well, at this point, you guys understand to say that to get the component, we just need the dot product. So the magnitude of F along CD will be equal to the dot product of F with a unit vector that runs from C to D. So this is what will give us what FCD is. But you know to say this is just going to be a number, straight out number. It won't be a vector. Now, how do we do that? Well, first we need a unit vector from C to D, and then we also need the force F in Cartesian vector form. To get the unit vector, we know to say this unit vector from C to D will be equal to a vector that runs from C to D. I can use vector, or I can say R for the position vector, C to D, and then divided by its magnitude. This is what will give me the unit vector. But the trouble comes just at getting what RCD is. Now, how do you get RCD? Well, let's see how it goes. So we come back here, and then let's see. For now, I'll remove the force F. We're just concentrating on just our the line CD. Now, the first thing that you want to see here is that in this diagram, they haven't specified your coordinate axis. Which one is X, which one is Y. So we stick to the general one, where we'll take X to be something that is going more like this, and then we'll take Y to be something that goes more like this, and then we'll take Z to be something that goes vertical, something like that. So this is the setup that we're going to follow, since that's the one that we've been using for the most part. But you want to position it such that it makes your life way easier. And the easiest way to do that is you can put it such that it's somewhere here at this edge. That's one way you can do that. Notice that I'm making my axis to coincide with some of the important lines here. Or if not this, you can get it and put it somewhere here, or you can even put it right here. For this example, we're going to be using it such that it is right at this point. So take this to be our x-axis. We'll take this to be our y-axis, and then we'll take our z to be this line. Now, in this case, how do we approach the question then? Well, the two methods I demonstrated. In one method, you need the position, the points, the coordinate of the point C and the coordinate of the point D. Now, one thing that you really have to understand here is where exactly is our point C and where exactly is our point D. One thing that I think one of the students who shared this question with me, their solution, they made a mistake, and the mistake they made was to position D along the y-axis. You have to see from the diagram that D is not along the y-axis. It is literally along this line. Let me draw it in blue. D is along this line. This is where D is. And the y-axis, if you wanted the y-axis, if a point like B here, B is literally right above the y-axis. So you have to see that B is right above the y-axis. So we can even argue to say that this plane here, the plane which is this side, this one here, this plane, it's literally standing on the y-axis. You can argue that. So that is what, of course, my thing is doing something else. So you can argue that that plane that I drew earlier is standing on the y-axis. But the point D is not on the y-axis. So that is one thing that you have to understand. So if you wanted to identify the position or the coordinates of the point C here, the position or the coordinate of the point C, how do you move to reach the point C? To reach the point C, look at what you have to do. If this is the origin, then to reach C, first and foremost, you can even say that first you go up. So to reach C, you go up. So this is in the z-axis. You go up until when you reach this edge. After reaching that edge, then you move now in this direction until when you reach the point C. So that is where C is. For the point C, we see one thing. In the y-axis, we haven't moved. We've only moved up in the z-axis, and then we moved in the positive x direction. So how far have we moved? We went strictly up from the bottom edge to the far edge. And we see to say that from here all the way to the bottom, it's a 5 plus a 3. So meaning we had to go up 8 units up in the z-axis. And in the x-axis, how did we move? In the x-axis, if you pay attention to the top here, in the x-axis, all we did was to move 3 units in the positive direction. So you can say in the x, we have a 3. In the y, we did not move, so that's a 0. And in the z, we went up, and that was 8 units up. So you can take those to be the coordinates of the point C. How about the point D? How do we move to reach the point D? Well, for the point D, first and foremost, the point D is right here. To reach it, what do we have to do? Well, let's say we're starting from the origin again. Want to reach D. D is right along this plane. This plane. This is where D is. Okay, again, drawing something else. So to reach this point, notice that first we can even say that in the x-axis, we go toward this edge. This is the first thing that we do in the x-axis. Then next, we move along this line parallel to the y-axis. So we see that to reach D, we actually get to move in the y-axis. So we go in that direction. Then lastly, we go up. Then we reach our point D. So notice that the movements then that we're making to reach D, in the x-axis, we went towards the positive x. We moved 3 units. In the y-axis, we went towards the positive y. So, and we went by 9 units, which is this. In the x, we said what? Sorry, that's not 3. Can you guys see that in the x, it's not 3 units? Can you see that in the x, it's not 3 units there?
Yes.
What's the correct one there?
It's 5.
5. Yes, 5. So thank you for that. So of course, if you're not seeing it, we are using this part here. So this is a 3 and a 2 here. The 3 which is here, it's a label from this point to this point. That's where the 3 is there. So be very careful when picking these values. So that's a 5 in the x-axis. Then in the y-axis, it's this 9 at the bottom here, and we're in the positive direction. Then lastly, we went up in the z-axis. How far up did we go? So notice that that's where this 3 comes in. We went up 3 meters up. So we're going to have F3 here in the Z. We're going up, so again, positive. Okay, now with this done, okay, I'm seeing I somehow erased the Z axis. Let me just bring it back. Okay, so this first part is done. We've got the coordinates. Now to get RCD, so we want the coordinates of D minus those of C, since it's final minus initial. So in the X, what was the final? For the point D, in the X, it's 5. So we have 5 here, minus where we're starting from. C, the starting point is 3, I mean. So we have a 3 here. So in the X, this is what we have. Plus, how about in the Y? In the Y, the final is 9. So we have a 9 here, minus the starting point. For C, in the Y, the starting point is a 0. So here, we're going to put 0 here. Then next, so this is in the J direction. Then plus, we check again the next one. The next one, the final in the Z, that's a 3. So you have a 3 here. Minus, for C, the starting point, that's 8. So we have 8 here. So this is K. So we simplify this. We get a 2 here. This becomes plus 9. This becomes minus 5. Okay, this becomes the position vector pointing from C to D. So we have ticked off this. The next thing that we need is its magnitude. So now we can get the magnitude of RCD. And to get this magnitude, you know how it goes. It's the square root of 2 squared plus 9 squared plus negative 5 squared. So this is going to be 4 plus 81 plus 25. What will be the answer here? So if it's not perfect, you can just add this. This is 29. 4 and 25 is 29, plus the 1, that's 30. So this is about 110, is it? Is this 110? I think it is. Okay. So lastly, we can get the unit vector from C to D, and we so to say it's the vector itself, the position vector, which is 2, 9 minus 5, 2, 9 minus 5, divided by the magnitude, which is root 110. So that this is now over this, plus, again the same, and then minus 5 over the same. So we have got our unit vector. So now we have the unit vector pointing from C to D. The next thing that we need is the force, the same force that we're going to be dealing with, this force. But we need to express this force in Cartesian vector form. So we know to say, for us to write it in Cartesian vector form, since we're only given the magnitude of the force F, is it so? So let's see, determine the expression. Oh, okay. We don't even know what the force F is. So they just want the expression of the force F. So we know to say the magnitude of the component FCD will be equal to the force, the vector force itself in Cartesian vector form, of course, then dot a unit vector pointing in that direction from C to D. So that would be the expression that they need. We won't get an exact answer because we don't know what the magnitude of the force is, and it's not given anyway. So all we'll do is we'll get a unit vector pointing in the direction of F, and then we'll also we already have the unit vector in CD, so get a unit vector pointing in the direction of F. That's the only thing that we need right now. How do we get that unit vector? Let's erase everything else, and let's go through this one more time. But this time I'll use the other method, the one I prefer, where you just say, okay, I'm starting from this point, I'm ending at that point. Okay, so to get the unit vector from, that's now, from A to B. So to get a unit vector, let me just highlight this so that we know what we're looking for when we come back for it. This is a unit vector from C to D. Now we need a unit vector running from A to B, the direction of the force. We know to say this will be the displacement vector from A to B divided by its magnitude from A to B. Okay, so we need these two, RAB and the magnitude of RAB. But how do we get it? Now we're going to use a shortcut. How does it go? Well, for the shortcut, here's what you have to do. Just start. You're moving from this point A. How do you move? Well, to move from that point A, in the y-axis, you're going towards B. Okay, I think for this one, it's easier to see it, I think perhaps with the coordinates. Yeah, I think the coordinates are much better. But in the y-axis, this is at 3, and then you're ending up at 5. So notice that the point B is 2 units above the point A in the z-axis. So in the z-axis, you have to see that this is 2 units above. But perhaps for you to be able to follow, let me just use the coordinates. The point B, the coordinates for the point B, what do you have to do? So notice at the point B, you have to first go, to reach B, you first have to move from here to this edge, and you move, this is in the y-axis, you move 9 units in the y. So I know this is going to be 9 units in the y. How about in the z? Going up, you have to move 5 units. And we have already reached B, so that's 5 units. Since it's up, it's going to be positive. Notice that we haven't moved in the x altogether to be at for the point B. So this is literally a 0. For the point A, what will be the coordinates? For the point A, what you have to do is, first, you move along the x-axis, and this is 5 units again, remember that? So you're moving towards the positive x, that's 5 units. Then next, you go up in the z-axis to reach A. Notice that for A, you haven't moved in the y-axis altogether, so that's a 0 in the y, but then in the z, we have a 3 going up, positive. So if we take the same method, the final point, which is B, minus the starting point, which is A, we see that for the first part, we end up 5 units up at point B, minus, we started 3 units up at A. This is in the I. Plus, if we go back again, in the Y, we end up 9 units up. This is in the, sorry. The X is 0 and 5. So it's 0 minus 5. Yeah, the one I did is in the Z. The one I did is in the Z. Sorry for that. So it's 0 minus 5 in the X, not this. So in the X, we have 0 minus 5. And then in the Y, we have 9 minus 0. So we have 9 minus 0, J, then plus. In the Z, let's see what we have in the Z. In the Z, it's now final 5 minus 3. So that is where the 5 minus 3 comes in. Okay. So from here, we now have minus 5i plus 9j. Then this is going to give us a plus 2k. So this is our AB. Now we get its magnitude. So we're going to have the square root of minus 5 squared plus 9 squared plus 2 squared. So that this is 25 plus 81 plus 4. You see that we're going towards the same answer we had earlier on, root 110. Any questions? Any questions there? Okay, so looks like we're okay. Let's just look at this. I hope you guys are following. You should be able to catch it in case I make a mistake. I shouldn't be allowed to make a mistake. So you guys should be able to observe them. Okay, so let me just verify this. To move from C, the shortcut now, the shortcut, how I would use it, to move from C to D, let me remove everything else. From C to D, what you'd have to do is, in the X, you move positive 2. So we had a positive 2 in the X. Yes, that was a positive 2i. Then in the Z, in the Y, I mean, you have to do this one. In the Y, you have to do this one. Let me just check one thing. That's okay. In the Y, you have to move like this up to here. That's 9. So it's 2i, 9j. Let's make sure that's the one. Yes, plus 9j. Then in the Z, okay, for this one, let's see, you have to go from here up to there. In the Z, you're ending up 9 units below. So that's not 9 units. This is 5 minus 5. Is it what we had? Where is it? RCB. Yes, 9 and then minus 5. Yes, that's what we had. So this is okay. And then the other one. So this is fine. We have 2 positive, 9 positive, minus 5 negative. So that's okay. The next one now, to move from A to B, I can say from A to B, first, we move from A parallel to the y-axis up to somewhere here. That's a 9. So in the y, we have 9j. And then in the z, you go up. This is at 3. You go at 5, so that's 2 units up. And then lastly, you go to B. This one now, it's going in the opposite to the x. The x would have been like this. Now we're going in the other direction. So this is negative 5. This is up, positive 2, and this is positive 9. So you have negative 5, positive 9, positive 2, which is exactly what we had. So this is fine. So we have RAB, we have its unit vector, we have its magnitude as well. We can get the unit vector from A to B. UAB becomes equal to the vector, that's minus 5, minus 5i plus 9j. Then the last one is plus 2k. This is divided by root 110. So that this is the same as minus 5 over root 110 plus 9. This is I. Then root 110 again. Then plus 2 over root 110. This is k. This is j. So we have everything that we need. So we know to say the force that is given from A to B will just be equal to whatever the magnitude of F is, since they've just given it as F, then multiplying this quantity here. This is what the force is. So you can even say that FAB is just equal to, yeah, I think it's fine just like that. Even if the force, anyway, I want to take the force inside. So this becomes minus 5F over root 110 I, then plus 9F over root 110 J, then plus 2 over root 110. There's an F here, and then we have the direction there, okay? So that now to get the component of F along CD will be equal to the vector itself, F along AB, dot the unit vector that points along CD. So this is what we have to do to get the component. So we know the force F along AB. This is the one. Sorry, I don't want to do that. Okay, yeah, I think this is okay. So this is the force F. Excuse. Now we're getting its dot product with, where's the unit vector along CD? It's here. Okay, so this is the dot product we're evaluating. So in this case, you know how it goes, like for like. This is going to be minus 2 multiply 5 multiply 2, we end up with a 10F. Then root 110 will multiply root 110. This will just be over 110. I hope you're seeing that. The I and the I will give us a 1. The 9 will multiply 9, we get 81. Then the F will come here. The J and the J will give us a 1. Then again, root 110 will give us 110. Then plus, again, 2 will multiply 5, we'll get 10. It's positive and negative, so this is going to be negative. So it's going to be negative 10. The F comes here, then over root 110 over root 110. This just gives us 110. So when you look at this, we can easily simplify this into just one term. For starters, these are like terms, but even if you don't say these are not all these are like terms here, so let's say these are the same, so just multiply by 2. But you can still just go right ahead and say it's over the same denominator. So get that denominator and just add the numerators. Minus 10F plus 81F minus 10F again. So that now we can just add these. So this is minus 20 from that, that's 61F over 110. So this becomes the component of F along CD, 61 over 110F. Any questions?
So can I just...
Can you?
The question.
The question.
Maybe
I'm not getting that.
erase the like the line that... Oh, okay. Oh no. Oh, thank you. I didn't see that F was along AB, so I was wondering why we were finding AB. I thought it was along CD.
Oh, okay, okay.
But I've set along AB, so it's okay.
Right. Okay, any other questions? Okay, so this seems like it's okay. So this is how you were supposed to work it out. And yeah, I hope you guys were able to follow that. There was this question as well. I sent a solution to this one. Were you guys able to follow it? Is there a need for us to present it? Or you guys were able to follow from the solution? Kangwa, yes?
I think I was a bit lost on this one.
Which one? This one?
The one on top, the one yes.
You were lost. Where? So we present it as well?
Just for the, yes, just for the one to question A, yes.
Okay.
Yeah.
Okay, so let's see what we're being asked here. So they're saying determine the following. The magnitude of the projected component of F, which is 300, acting along line OA. So again, it's the same concept as before. They want the projection of F on the line OA. So we know we're going to use dot product here if it is possible. And then in the second part, they're saying the magnitude of the projected component of F 300 along the X and Y axis. So here now they're saying we project the same force on the X and the Y component. Again, dot product. But for this one, where we're projecting to the X and Y component, it's even going to be much, much easier to evaluate. The tricky one is going to be here for OA, because OA is something that we'll have to really, really evaluate. Because if I asked you, what is the unit vector that points in the x-axis? What are you going to say?
It's going to be 1.
1, not even 1, I. That is the unit vector pointing in the x-axis. So to find the projection of the 300 in the x-axis, we'll just get the 300 expressed as a vector, then dot it with I. This will give us the answer. To get the projection of the 300 in the y-axis, we'll express the 300 again in Cartesian vector form, which is the same as what you'd have from here. And then now just get its dot product with J, and that will be the answer. So we see that this one is really, really, really straightforward. But the tricky one is OA, because OA is not I, it's not J.
Can you repeat that again?
Okay, we are going to do it still. I'm just trying to lay the foundation. I will do it, so I think you'll be able to follow it when we do it. Okay, but literally I was saying, to get a projection of a vector onto an axis, we always get the dot product of the vector, which we're trying to project, dot the axis, a unit vector pointing in the direction of the axis where we want the projection to be made. But for the x-axis, a unit vector pointing in the x-axis is I. There's no need for us to start trying to find it. It's just I. And the unit vector pointing in the y-axis, it's just J. There is no need for us to start evaluating. So to get the projection of the force F in the x-axis, all we need is the force F in Cartesian vector form. The unit vector in the x-axis is already known as I. So just get the dot product of the two. The same thing in the y-axis. We'll still evaluate this so you'll still be able to see. But let's begin with the first one. For the first one, we want F along OA. But first, let's find where O is. OA is. O is here. A is here. So the axis we're dealing with is from O to A. So this is what we have. So let's find a position vector from O to A. Let's find this vector, ROA. How do we do it? ROA. So we're starting from O, we're going to A. But look at how it goes. Again, use as much of these lines as possible because they tell you when you're going up and when you're going down. In this case, we can tell to say that to move from O to A, in the x-axis, you go like this. You move up to here. This is not in the x, in the y-axis. This is what you will do. Then the next thing is, how about in the x-axis? In the x-axis, you know that you start from here, you reach this point. But have you reached your point A yet? You haven't. You literally have to continue this side until when you are literally just below the point A, which I think is somewhere here. Then once you reach this part, then you go up. So I'm trying to draw a vertical line here. So let me use this part. And then just move this one. Move it to here. So this is literally what we have to do. But let me draw this short one here in a different color so that we know to say this is something that we have to find. So if I wanted to find ROA using the shortcut, in the x-axis, in the y it's straightforward, but in the x-axis there'll be this region here that is a little bit tricky. We're not given what it is, would have to find it. You'll see how we find it. But first, in the y-axis, we know we cover this 300 millimeters. So in the y, we have the 300 J, and it's the positive y. So for now, let me just put x here, x in the I. Then in the z-axis, we go up. Again, we are seeing this up is not really given. We don't know what it is. But let's try to find these two missing pieces. To find them, we're going to utilize what is being talked about here, this side. Okay. So let's see what they are saying here. So we have this part. Okay, is there any other piece given? Let me see if there is any other piece given here. Okay, so we have this 300. Okay. Okay. So we have this line here up to this part. It ends there. But you have to see that the triangle that comes from here, this part here, it's a right angled triangle. And the hypotenuse here is given as 300. Now, the other thing that you have to see here is that this triangle, let me move this. I want to draw it better. Or I can get this line here. Let's put it there. And then we have this one here. Okay. You have to see that this angle that has been formed, or this triangle, it is a right angled triangle. And the right angle is here. This is where the right angle is. But what angle are we going to use here? To understand the angle that you need to use here, you have to take advantage of what is given from the get-go here. You can't use this. It's not clear how you use that one. But there's something else that you can use. That is this angle here. Notice how that angle is being given. This angle is being measured how far away this arm is being rotated from the vertical. But you know to say this is a right angle. This is the right angle. So if you're told what this piece is, then we can predict what this part is. And once we know what this part is, well, it's the same as this part. So I hope you've got that part. Do you have any question there?
So can you repeat again?
Okay.
Or now you get the angles.
Okay. So the key part here is you have to observe that this, let me draw it a little bit. This line here is vertical, more like parallel to the z-axis. And this is parallel to the x-axis. Then the angle, the 30-degree angle that is given, that 30-degree angle, it's how far away this line has rotated from the z-axis. So this blue line here, how far away it has rotated from the z-axis, that is what the 30 degrees is. Now, notice that this triangle that I have made at the bottom here, this triangle, notice that this triangle also depends on the bottom angle, which is here. Do you see that?
Oh, yeah, yes.
So in other words, by knowing what this upper angle is, because the upper angle this side is given as 30 degrees, by knowing what this is to be 30, we can easily say, well, this is forming a right angle. So if that is 30, then the one below has to be what? 60. This is 60. If this is 60, then this one here also has to be 60. We get that, right? With the 60 now figured out, we can easily use the hypotenuse, which is given as 300, because this part is given as 300. We can use the 300 and the 60 to determine what this small piece here is, and also to determine what this small piece is, because this small piece will be the one this side, the vertical one, will be telling us what the Z component is, while this piece will be added to this 300 to tell us how far we move parallel to the x-axis. Is that okay? Let's determine what these values are. I'm going to get this triangle, but I'm just going to draw it a little bit bigger. And I'll draw it as if you can see it from the side. Let's do it as if you can see it from the side, so that this is my hypotenuse. This is the piece parallel to the x-axis, and this is the piece parallel to the z-axis. We just saw to say that this angle turned out to be 60 degrees. The hypotenuse, when you look at this, let me just pull out this part. If I just pull out this, you can clearly see to say that the question gives you the hypotenuse here as a 300. So if I was to get this and take it here, you can see that that's my hypotenuse, which is given as 300 millimeters. So with my hypotenuse figured out as 300 from the question, now we can easily get what this piece is and what this piece is. And this is my side 1, this is my side 2, so that if I can come here, you can see that this is my side 1 and this is my side 2. The side 1 is side by side with the 60 degrees. That's why I've labeled this one as 1. It's the one side by side with the 60 degrees. Next up, how do I find these pieces? You see to say the side 1 is side by side, so it is adjacent. And if it is adjacent, we use cos. So it's going to be the vector itself, or the hypotenuse, which is 300, then cos 60. And you know what cos 60 is, right? What is cos 60?
Zero point five.
0.5. Then 0.5 by 300, that's 150, right? So this reduces to 150 millimeters. So we now know what this piece here at the bottom is. Because remember, we are trying to move from here, from this point, the origin, until when we reach just below our point A. We knew that this was 300 up to here. We knew that this was 300, but we needed to know what this one was. Now we know that this piece is 150. So in the x-axis, it's 300 plus 150. So in the x-axis, it's 300 plus 150. So this one that I didn't know here, well, now we know it. It's 300 plus 150, which is 450. And there's one more thing that I've done here deliberately. Can you guys spot one more thing I should add here?
Wait, how is it 300 plus 150 again?
Okay. Okay, so how is it 300 plus 150? Well, we have to see this line here. Point A is literally right above this point. This is where A is. But instead of giving us the whole thing, the question told us to say that from here to here, it's 300. Instead of giving us what this piece was, they instead gave us, they took it up. And not up to there. They made it something like this. So I'm trying to literally just show you to say that this part You got it? So we have, this is where we're coming from. Instead of continuing it, they are taking it up. You see that? But the point A is literally above this point. So to get how far you have to move from this point, you need this distance up to there. But for this distance, all you have is up to here, because up to here, it's given as 300. But this piece here, this piece, this is the one that we were finding. This is the 150. Because this is what makes a triangle, a right-angled triangle with this. Do you see that?
Yes, I see it.
So in the end, to get the distance all the way from here up to there, it's 300 plus 150. Do we have a question?
Okay.
Isn't it negative?
Exactly. That's the thing that I said I left out. The positive x is in this direction. Notice that here we are moving from this point, going in this direction. So this is in the negative x. So this 450 has to be negative. So we've sorted out the x component, the y component. Now we go to the z component. For the z component, we have to go up from this point, going vertically upwards. And we see to say that this piece is just the hypotenuse of this triangle, not the hypotenuse, the vertical of this triangle, which is this side. To find it, of course, we're going to use sine because they are opposite. It's going to be the 300, then sine 60. This is what is going to give us the vertical part. So what is 300 sine 60?
259.81.
259.8. 0.8 what? 1. Since it is up, it is positive. This is in the k direction. So this sorts out ROA. Any questions? Okay, ROA is sorted out. The next one that we now want to do is we now need to express the force in Cartesian vector form. Because remember, to get the projection, again, we need to get the projection along OA. We need the force itself, dot, wherever the force is, then we'll get its dot product with the unit vector pointing along OA. So here we have the displacement vector along OA. Let's get the unit vector. To get the unit vector, we need the magnitude first. So this is going to be the square root of minus 450 squared plus 300 squared plus the 259.81 squared. What would this give you?
$600.
600. So now that we have the unit, the magnitude, we can easily get the unit vector from O to A. This will be minus 400 over 600 plus 300 over 600 plus 259 over 600. So of course, now we just simplify this a little bit. So the first one, what will this reduce to be? 2 over 3, right? Negative 2 over 3.
Yes. Yes.
The second one will just be 1/2. The third one, this is J. What would this be?
It's given a big number.
It can't be a big number. It's a small number with a lot of decimals, 0 point something. It's 259.8.
It's giving something like 0.43.
Okay, that's 0.43 what?
0.433.
Okay,
Regarding
0.433 in the K direction. Okay, so with this done, we now know what this is. Now we have the force to deal with. Okay, so let's see how we get the force. So to get the force, again, we're going to express the force in Cartesian vector form. We need to multiply the magnitude of the force and the unit vector pointing in the direction of the force. This will give us the force in Cartesian vector form. In the previous example, we didn't know what the force was, so we just left it as an expression. But in this question, we are actually told what the force is. So we have to use whatever that is. So in this case, we're given the direction of the force. So you shouldn't confuse what was happening before to what is happening with the force. For the force, make use of what they're giving you here. This part, use it. And if you look at what they're trying to simulate here, they're trying to tell us something where this line here, it is actually a line parallel to the y-axis. This line here, it's actually a line parallel to this line here. So we're forming such type of a shape. But the key part is that this is parallel to the y-axis. Okay, I need to plug this in. Okay. Okay, so we need to break down this to get its pieces. And we see to say that this force, what components are we going to have from this force? Well, the first part is that we can easily get what this side is here. We can get what this side is, and we can easily get what this side here is, what it is, right? So strictly speaking, we can easily get the best part, the one parallel to the y-axis. This one is going to be the easiest. Since we know this is, let's see, do I want to use pieces, steps, or we can just get the components using sine and cos? Yeah?
You're not sounding very clear.
Okay. Look at this. We have a triangle here. This triangle is this side, and this side, and this side. So this is the triangle that we have. And the angle here is 30. Now, how do we work it out? The hypotenuse of this triangle is 300 newtons. We know to say this is a right angle here. Now, with this figured out, how do we proceed? Well, we can easily use cos and sine to get what this is and also what this is. Now, notice the first one, this part at the bottom. This part at the bottom is side by side with the 30. So it is going to be related by cos. Let me put it somewhere here. So the one at the bottom, we have the 300 here, and then we have the 30 here. 30 degrees. The one at the bottom is adjacent to the angle. So we're going to use cos for this one. And it's going to be 300, the hypotenuse, then cos 30. But do you see what this actually gives us? Who sees what this gives us? What does this give us? Which component does this give us?
Giving us this is 9.8.
This is giving us this side.
Gives the K component.
Check this. It's giving us a component that is along this axis. And when you look at this axis, which axis is it? Don't you see that this is the y-axis? So when we get this side here, the one at the bottom here, this side is actually just the y component. Don't you see that? So a y component is parallel to the y-axis. An x component is parallel to the x component. And you see that this is parallel. Of course, my lines are not perfect, but this is approximately parallel to the y-axis. So what this is actually giving us is the y component. So that is what this is giving us here. So this is the y component. But how about this piece here? What is it giving us? Because so far, we have seen to say that our force F, in terms of the components, we have figured out what the y will be. So let's say we have the x here, plus the y, we've just seen that it will be 300 cos 30. It's positive because this component is pointing in the positive y, the same as this direction. But how about this piece here? Because we need the x and the y components, now the x and the z component. The only side that we can find using this triangle is this piece here. But does it give us the z, the y the x or the z? Let's evaluate it. We know to say it will be given, it will be opposite to the 30. So it will be given by 300, then sine 30. Again, sine 30 is half. So sine 30 is half. Half means half times 300, that is going to be 150. So we know that this part here will just be 150. Now, let me ask you this tricky question. Is this the x component or the z component? Because those are the two missing. So is that the x component, or maybe it is the z component? What do you think?
Can I see it again?
Okay, just a minute. Is it an x or a z component?
I think it's none.
It's none. Nice. It's not an x, it's not a z. But in fact, you have to see that this component or this line, it is actually a bit in the x and a bit in the z. In other words, if I was to remove everything else here and just leave that component, this component will be such that, picture it as if it's literally right here, strictly in the x and z axis. So this one now only has an x and a z component in, and if you can look at it, the angle it makes with the z axis, don't you see that it's the same as this one? How far away this is from the z axis? Do you see that? This line, it's parallel to this side. That's why they even drew this for you. These two are parallel, as in this is parallel to this line. So the displacement of this line from the z-axis is the same as what we had here. This is also another 30 degrees. Given this, then we can easily determine the x and z component. Because if this is the z-axis, that vector is something like this one here. So if this is where the vector is, the question tells us to say that the angle here is a 30. So if we have the x-axis, let's say as something like this, if this is where the x-axis is, then we can easily determine the x component and the y component. So let me, I think I have, we can go yellow. The z component will be here. And the x component will be here. So from here, we see that this side, the vector itself, if you recall, we found that this piece here was going to be 150. And it's the one that we just determined, so the angle between this side and the y-axis, the z-axis is 30. So I've come this side and I'm saying this is 150 newtons. So since the 30 is opposite to this piece, I'll be using sine there. So it's going to be 150. Since I'm using sine, it's going to be sine 30. And notice that this is pointing in the negative x, pointing backwards like that. So this has to be negative. For the y-axis, it's pointing up, so it's positive. It is side by side with the 30, so they are adjacent. So we're going to have 150, then cos 30. Notice that now we have completed this. The force F in Cartesian vector form, it's going to be the x component, it's negative 150 sine 30. Then the y component, we found it earlier on. The y component, we found it first. It was 300 cos 30. Then lastly, the z component, this is in the J. The z component, we've just seen that it is 150 cos 30. So these are the components. You can even evaluate them. What would be the first one? Just half of 150. Is it negative 175? No, not negative 175, negative 75. So you guys can verify this. Then we have 300 cos 30. I have too many negatives here. This was not negative, this was positive, positive 300. So this is plus 300 cos 30. So what is 300 cos 30?
In 259.8.
So we have 259.8 J. And then the last one, 150 cos 30.
129.9.
129.
Point?
9.
Okay. So we now have our force. So to get now the projection of F along OA will be equal to F dot the unit vector along OA. So we know how it goes. The force F, we've just found it. Then the unit vector, we found the unit vector earlier. Okay, so this is what we have. So now we need the dot product here. So the 75 multiplies 3 over 2. So what are we going to get there? Is it 50? What will be the first term? 75 multiplying 2 over 3. Is it 50?
No, it's giving 112.5.
1?
You said divide, or you said multiplication, sorry.
Is it 50?
Yes.
50. Negative and negative
Yes,
will make
50.
this positive. Then we have 259.8 multiplying half.
$129.
129.9. Then lastly, 129.9 multiplying 0.433.
$56.25.
Notice that these don't have direction. There's no I, there's no J, there's no K. The dot product of two vectors is a scalar quantity. So when you add this, what do we get?
We get 236.15.
236.15. Okay, this becomes the force F along OA. Now, the next question is, what will be the units of this value? Well, everything we are breaking down was the force, and the force was in newtons. So we expect this to have the same units as the force that we're dealing with. Okay, so just review. Is this the correct answer? So we expect this to have the newtons as well. So just we can go through the math and make sure that this is actually what you expect to get. Okay. Yeah, looks okay. Okay. So yeah, you guys can verify this and just make sure it's fine, but otherwise everything else is okay. So in part B, now they were asking that, let's see that. They want us now to determine the magnitude of the projected component of the force F. The same force, now it's the same force here, the same 300. But now they're saying acting along the x-axis. And then in the next part, along the y-axis. Well, this is very, very easy. We've done the heavy work here, because let's get the force. The force F is here. We already did determine what the force F is. This is what the force F is. To get its projection along the x-axis, all we need is a unit vector pointing in the x-axis. And we know to say the force in the x-axis, a unit vector, first we have the force itself, F dot, a unit vector pointing in the x-axis is just I. I is the unit vector pointing in the x-axis. So we know to say if we are to get the dot product of this and the unit vector I, notice that it's just I multiplying the 75. All these will not be there. There'll be zeros because we only have I. So it's like for J we have 0, for K we have 0. So it will only be I multiplying negative 75. So f of x will be minus 75. Notice that it's the same case for the projection in the y-axis, because a unit vector pointing in the y-axis is J. So it's going to be the force itself, F, dot a unit vector pointing in the y-axis, which is J. So if you look at this, J will look at this value F, and it will only multiply the one that has J here. Everything else will be zeros. So it will be 259.8. So this one will be 259.8. Then we're done. Any questions? Okay, so yeah, I think we can end here. If there are any questions, you can forward them. I did manage to record this. I think I will upload it as soon as we're done. All right, guys, have a good night. We'll see you tomorrow night.
Good night.
Good night.